This is the video for section 8.1 notes, slides 5 and 6. All right, so we are looking to find the area of the region bounded by y squared equals 4x and 4x minus 3y equals 4. All right, so first of all, what I want to do is I need to come up with this graph. All right, so we need to realize that y squared equals 4x can be rewritten as either y equals plus or minus the square root of 4x. So that would be like the top half of a sideways parabola and the bottom half of a sideways parabola. Or I could rewrite it as x equals 1/4 y squared. Now, if it's an x equals 1/4 y squared, we should realize it is a sideways parabola facing to the right, and the 1/4 would actually stretch it out and be like wider than normal. All right? Now, what about 4x minus 3y equals 4? That is a line, so we could solve it for y. We would subtract 4x, so negative 4x plus 4, and then divide by negative 3. And so we could say that this is 4/3 x minus 4/3, right? So we would know that this would be a line with a slope of 4/3 and a y-intercept of negative 4/3. Right? But we could also solve it for x, right? And we could say, okay, well then, if I want to solve for x, I would add 3y and divide by 4. So 3y plus 4 over 4. Or we could say 3/4 y plus 1, right? Now, there are reasons, obviously, for solving for y, right? Because that would be helpful for drawing a graph. But there are also reasons for solving for x, which I hope to show you. All right. So now, what we want to do is we want to look at this region a little bit more. So we draw this picture. All right. Now we can very clearly see that there's going to be 2 points of intersection. All right. But we don't know those yet, so we're going to have to solve for those. All right. So let's solve for the points of intersection. So how do I do that? Well, I have to set the two equations equal to each other. All right. So how do I do that? Well, I could do the y equals versions equal to each other, or the x equals. So it turns out that actually setting the x equals, so 1/4 y squared equals 3/4 y plus 1, it's actually a little bit easier to set those two equal to each other to find the points of intersection. All right, so first thing I'm going to do is I'm going to multiply by 4. So I got y squared equals 3y plus 4. And then it's a quadratic, so I'm going to solve by getting everything on one side. So y squared minus 3y minus 4 equals 0. So now we want to factor, if possible, otherwise completing the square. All right, so this one is factorable, y minus 4 and y plus 1. So that means that y equals 4 or negative 1. So what have we just found? We've just found the y values of the intersections. All right, so this one is something comma 4, and this one is something comma negative 1, right? So how would I find the x values that correspond to those? Well, if I take one of the equations, so I'll take this one, x equals 1/4 y squared. So x equals 1/4 times 4 squared. Well, that would be 1/4 of 16, which is 4. So that means this point up here on the right is 4 comma 4. And the other one, x equals 1/4 negative 1 squared. All right, so negative 1 squared is just positive 1, so 1/4 of that is just 1/4. And so this point is 1/4 comma negative 1. All right, so now I know the intersection points. All right, so now what I want to do is I want to think about this region. All right, so you can see the region here, but I'm actually going to zoom in on it so it's much more clear when I'm drawing my picture. All right, so let's take a look at this region. All right, so now what I want to do is I want to draw a rectangle like we did when we were doing Riemann sums and stuff. So the rectangle here, all right, has a thickness of dx. Okay, now what I want you to realize is, remember when we were doing like Riemann sums, we would draw these rectangles and we'd say, okay, we're going to add all these up. Now I'm just going to draw one here. Okay, so if you go off of, like slides 2, 3, 4, right, we're thinking, okay, well, the upper boundary of this rectangle is like our f of x, and the lower boundary is like our g of x, right? So we can say, oh, okay, well, the upper boundary is this curve, and the lower boundary is the line, right? Let's say I drew the dx over here, okay? Or over here, or over here, right? All of those rectangles have the curve as the upper boundary and the line as the lower boundary until you get over here. All right, now you see over here, the upper boundary is the curve and the lower boundary is the curve. So keep in mind, this curve here is the positive root 4x, right? But then this curve down here is the negative root 4x, right? And the line obviously is the line no matter where we are, all right? So what we actually have going on here is we have two distinct areas. All right, so I'm going to draw this little line here. All right, so we're going to cut this in, well, not in half, but into two different regions. So I've got this region on the left here, right? And then I have this bigger region on the right. All right, so what I want to do is I first of all want to talk about, let's say, the area on the left. All right, so the area on the left. All right, so let me zoom back out. All right. All right, so if I zoom back out, all right, the region on the left, let me go one more out. All right, so the region on the left, all right, we want to integrate, all right, something with respect to x. Notice the dx, that's like the dx, the width of the rectangle. All right, so I'm going to integrate something with respect to x. Now remember, we're going to take the f of x, the upper boundary, minus the g of x, the lower boundary. All right, so what is the upper boundary? Okay, the upper boundary, well, is the positive root 4x minus the lower boundary. What's the lower boundary? Well, the lower boundary of that little part on the side is actually negative root 4x. Okay, now I used parentheses around the root 4x and the negative root 4x, but those are actually not necessary. All right, and if you think about it, I'm subtracting a negative, so this would actually become root 4x plus root 4x, which would just be 2 root 4x. All right, now, okay, if I go back to that little area here, I want to think about what the limits of integration are. So how far to the left does that small little region go? Well, it goes as far left as 0, right? That's like the vertex of the parabola. All right, how far right does it go? Well, it goes to that black line that I drew, which is 1/4, right? Remember, it's the x value, right? Because we're integrating with respect to x. All right, so that's the area of the region on the left. All right, but then plus this bigger region on the right. All right, so now I'm going to integrate, once again, something with respect to x. All right, so I'm going to take the upper boundary of the region minus the lower boundary of the region. All right, what is the upper boundary? Well, once again, it's that curve. It's the positive root 4x minus the lower boundary. All right, what is the lower boundary? Well, it's the line. So it's the 4/3 x minus 4/3. So 4/3 x minus 4/3. Now notice, I used the parentheses here. Okay, the first set of parentheses around the root 4x doesn't really matter, but the second set does, because I would be distributing that negative sign. So what I do in general is I just always put the parentheses, and then if they matter, great. If they don't, well, whatever. I'm not going to change them. All right, so now how far to the left does this bigger region go? Well, it goes to the left as far as 1/4. And how far to the right does it go? It goes to x equals 4. Now remember, these limits of integration are x values on the graph because we're integrating with respect to x. All right, so now, okay, that would be the area, but it took 2 integrals. All right, so now what we want to do is we want to consider it from a different perspective. All right, so I'm going to zoom in once again back on my picture here. All right. And so now we're taking a look at the picture. So now what I want you to do is I want you to imagine tilting your head 90 degrees to the right. All right, so if I tilt my head 90 degrees to the right, now let's say we draw a rectangle on there. All right, so now I draw this rectangle here. All right, or what if I drew it over here? Or what if I drew it over here? All right, now if these other rectangles had a width of dx, okay, now these ones, if you're looking on the side, these actually have a width of dy, right? Because the thickness is an x value, now the thickness is a y value, all right? So now, if you're looking at this, okay, what is the right-hand boundary of all of these horizontal rectangles? Well, you can see the right-hand boundary, no matter where I draw it, is always going to be the line. And the left-hand boundary is always going to be the curve. And so, if I zoom back out, all right, we could actually integrate this, but only with one integral. All right, so let me go one more. No, too far. All right, so what I'm going to do is I'm actually going to write an integral that we're going to integrate with respect to y. All right, so now, it's very important that we understand that we're using a dy. So what does that mean? That means we can only have y's in my integrand. Notice, when I integrated with respect to x, x is the only variable in my integrand, right? So now if I'm integrating with respect to y, y is going to be the variable that's in my integrand. All right, so now, okay, when we think about like the upper boundary or like the f of x minus g of x, now we want to think, okay, if I tilt my head to the side, what is the upper boundary of the dy? Well, it's the line, right? But remember, it's not the y equals 4/3 x minus 4/3 version. It's actually the x equals 3/4 y plus 1 version. Remember, it has to be with variables of y, so it has to be the x equals version, minus the lower boundary. Remember, now the lower boundary is this parabola, right? And remember, in the x equals version, the parabola is 1/4 y squared, right? And so I have the upper boundary minus the lower boundary, and in this case, those extra parentheses don't really do anything, but I'm going to leave them anyway. All right, so then what about the limits? All right, so now I'm integrating with respect to y. So y's are in my integrand, which means the limits of integration need to be y values. So on the graph, what is the lowest y value? So if I'm at this point, the y value is -1, and if I go up to the other point, the y value is 4. And so what we're doing here is we're actually finding the area, but with respect to y. And if you were to calculate both of these integrals and add them together, it would be equal to that one integral. All right. And so the first way we did it was with what we call a dx cut. And the second way we did it was what we call a dy cut. You need to be able to do both, but in this case, the dy is easier. All right. So then let's take a look at slide number 6. All right, so it says find the area of the region bounded by y equals x cubed and x equals y squared minus 2. All right, so if we do that, all right, we're going to draw this graph. Now, you should know what y equals x cubed looks like, and you should know what x equals y squared minus 2 looks like. All right, so if we have that, all right, y equals x cubed looks like this, x equals y squared minus 2 looks like this, right? All right, now, what do we want to do? Well, first thing I do is I want to zoom in and I want to think about what we should be using, a dx or a dy. All right, so now as we do this more and more, you'll get pretty good at it. So if I draw a dy here, right, or a dx here or here, what do you notice? Well, if I draw a dx in those two locations, this one over here, the curve, right, this y equals x cubed is the lower boundary, but over here, this other curve, the parabola, is the lower boundary. Okay, but if I use a dy, no matter where I draw the dy, the right-hand boundary is always the y equals x cubed, and the left-hand boundary is always the y equals x squared. All right, or the x equals y squared, right? All right, so let's zoom back out. Too far, probably, right? No, that's good enough. All right, so now what we want to do is we want to integrate with respect to y. All right, so that's what we're going to do. So we're going to integrate with respect to y. All right, so now I have y equals x cubed, but if I'm integrating with respect to y, I need an x equals equation. So x equals the cube root of y, right? And over here, x equals y squared minus 2. So I would leave it as x equals y squared minus 2 because it's already in x equals form. All right, so now I'm going to take the upper boundary. Now remember, if you tilt your head to the side, the upper boundary is that y equals x cubed, but it needs to be in the x equals form. So cube root of y, all right? And then we subtract the lower boundary, which is this quadratic, which is y squared minus 2. So remember, if we're integrating with respect to y, then we only can have y's in our integrand, which means that our equations have to be in x equals form. So I have the x equals y cubed and the x equals y squared minus 2. All right, so the next thing that we need to do, all right, is we need to figure out the limits of the integral. All right, and so if we do that, right, well, this is one where we cannot do it algebraically, or if we do, it would be a 6th-degree polynomial, which is actually pretty annoying. And so we're not going to be able to do that. And so what we need to do is we need to use our calculator. So what are we going to do? Well, we have to type into our calculator the graph so that we can find these points of intersection. All right, so y equals x cubed, right? So that's just easy enough to type in. But what about this one? X equals y squared minus 2. So we are going to type in, well, we have to solve for y, so we add 2 in square root, so y is equal to plus or minus the square root of x plus 2. So now we're actually typing 3 things. We get y equals the positive root x plus 2, and y equals the negative root x plus 2. All right, and so now we need to find this intersection over here, which is going to turn out to be -1, -1. All right, and then we need to find this intersection here, which is going to be, I can't remember off the top of my head. All right, but it's going to be like 1.2 something, 1.3 7 something. All right. All right. So let's go ahead and find those values.